Okay, I think that most of the people probably had come, so you can try to share.
Okay.
Yeah.
Uh, so I mostly will be drawing, but here I got pictures and plan. Plan is mostly for me.
Yeah. Okay. So just be aware that probably most of us heard about P and NP, but if people heard about TF and P, probably they already forgot everything like me.
Yes, and
So
yeah,
you
I'll
should be
start from
very
explaining
slow,
TFNP.
and you should address to idiots in your talk. So be very calm and kind.
Yes. Okay,
Okay.
let's start. As it was said, main object of my talk is TFNP. And what is it? It's translated as total functional NP. And well, from this, first of all, it's functional, so it's a class of search problems. And with such properties. First, total means that for any input, no, search problem, that means answer is not just 0 or 1, but
So search
it's a
problem is a
string.
binary relation on strings or something else.
Yes, not binary.
Not binary.
No, functional.
No, I guess
So
there is some x and you want to find some y, which
yes,
is some in some
given
relation
x,
to
we
x.
want to find y. Yes. So
But you
not
assume that
just
y
0
is
or 1.
unique or not?
Not usually not unique.
No, that's what I'm saying. That it's a binary relation. Binary relation just it's бинарные отношения на словах. So just for every x and y, we know whether x and y are in this relation or not.
Yes, on pairs.
On
Okay,
pairs,
yes.
yeah.
Yes, so we require totality. Total means for any
For
x,
any.
for any x, there
For
is
any. No.
for,
You just you draw exists.
oh no, for any x, there is y such that
Y.
xy is an, no,
This.
this is condition of R laying in
Yeah.
TFNP. First totality. Second, NP, this answer should be easily verifiable. And so there is a verifier such that x, y in R when verifier from x, y equals 1, where we require that verifier is polynomial in length of x. And also we require that for any x, a set of y such that the correct answers, it must be all answers must be limited in size by some polynomial. So
So for every r, there is a polynomial.
yes,
And that can be different for different r's, but it's a part of the description of r.
yes. So
No, wait a bit. Y of x is a set. Do you
no,
really mean that the
not size
cardinality
of
of this
set.
set
True,
is...
not size. Not size. For any y in x, length of y is limited. Yes. Amount of answers can be big. No,
Number
well,
of answers can be
number of answers
exponentially big.
can be, yes. So
And the verifier is non-deterministic.
No, 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 no. Verifier is deterministic.
Yes,
V is in P.
deterministic.
V is in P.
The verifier very similar to one in NP.
No, 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 not in NP. Verifier is in P. Don't confuse
To
me.
verifier used in definition of NP.
Yeah. But also, it's not important whether we write requires the verifier to be polynomial in the length of x or polynomial in the length of x and y together.
Yeah,
Because
given this
anyway, if y
condition.
is long, we know that it cannot be in R.
Yes.
Yeah, but now TF and P is a subset of P.
No. No, it's somehow it's subset of P, but we consider just the search problem related to R. The problem is for X, find some Y. And this problem is not polynomial, of course.
Okay.
But the goal is
Yes.
polynomial. Yeah.
It's very NP-like that answers can be easily checked, but finding them isn't so trivial. So, and second thing we need, if we have class, we need reductions, or else it will be boring. So how we define reductions? In this case, reduction is not one function, but two, f and g. And how they work? Let's assume this is a reduction from R to S. So, and let's assume we are given input of R, X. So we want to find answer. So what we can do, we can use function f to convert this X to the input of S, and no. Then if we somehow find correct answer, so if f at x and o in S, then we can.
So let's not use 0 or O. It's very confusing. Let's try something else.
Yes, but okay, let's call it y, but I'll let it transition to O because it's widely used in black box model.
But why? It is output, or what? It's O for what?
Why is
no. Why the letter O is used? Because it's short for output.
I don't know why.
Okay.
It's not probably not because answer sounds like ответ in Russian. Probably there is other reason why. Oh, for me it's mystery.
No, but there is output. There is
Well,
input
maybe.
and output.
Yeah, yes, probably it's output.
Anyway, so you require that then you use G.
Yeah, then you can use G to get answer to the first search problem. G given O and X gives a new answer.
Okay, now if you cannot use Y, just use O. We will tolerate this.
It's impossible.
Okay. So if you are a physicist, it will be quite natural, because if you denote the mass by A, they will be completely confused.
So,
excuse me, may I ask a question?
Yes.
Yeah, why do we study only total relations? Why do we need totality?
It's it's a big question. Simple answer: it's easy to study them because in some way.
I mean, what is wrong if you remove totality?
Definition of reduction becomes more difficult because you need to account for cases when there is no correct answer. many interesting search problems lie in TFNP, so it's interesting to characterize TFNP.
No, probably you can try to define, consider non-total relations, but then you should ask something. Imagine we have an input and there is no output, and so if this machinery provides some answer, which is of course wrong, it's okay or not. Maybe. So do people consider another class for non-total
Yeah, but there is class
relation?
FNP, right? Without
Yes, there is class FNP.
Oh, so it has some definition, but
Yes,
just
there
we
is.
don't want it for today. We consider total
Yes,
problems.
well, in FNP, you have yes, if our machine answered there is no answer, we can't verify it, and it's quite sad.
okay, yeah, it makes sense. Okay,
And
thank you.
But anyway, no, it's there is nothing bad in considering the class
yes,
FNP. It's but just you are not obliged to do it, but you should not blame the people who do, because why they also have some.
May I add a bit about FNP? So basically, FNP is very similar to NP. So for instance, P equals NP if and only if FNP equals to FP. And also NP complete problems are transmitted to FNP complete problems. And then in TFNP, there are no complete problems unless NP equals co-NP. So there is some theorem. And this is why there are many subclasses in TFNP that are defined by particular complete problems in these classes. And so further we'll talk about these subclasses.
yes, as it was spoiled. TFNP, the problem with TFNP, there is no complete problem unless NP equals co-NP. So how
Can
to
you
research?
prove this? It sounds interesting. Why?
Once again, so if there is a complete problem, then NP is equal to co-NP.
If there is a complete problem, then NP is equal to co-NP. Okay, why?
So
Imagine there is some complete problem. So what?
let's think. So I had
Probably I talked a wrong thing. No, the truth is that if some TFNP problem is complete for NP, is NP hard, then NP equals co-NP.
If
what does it mean that the problem is complete for NP?
Yes, if a TFNP problem is NP hard, then NP
what
equals
does it mean,
co-NP.
NP hard?
You can reduce an NP complete problem to that problem.
But NP is decision problem, and how do you understand the reduction?
Well, I mean, you give input, and from the output, you can decide whether the formula is satisfiable from any solution.
Yes, just like here, but the function g returns not the solution, but the fact whether it exists or not. So if R is NP, then the scheme proceeds by the same. So there is function f and the function g, and g returns just 0 and 1 whether the solution for NP problem exists.
But and if it doesn't exist, then what should happen?
If it doesn't exist, then g must return 0. If it exists, then g must return 1.
No, but then it's kind of this is okay. Okay, maybe it would be an interesting thing if we go into this and cover more about this connections between TF and P, F and P, and
So
then
once
P.
again, so if you reduce SAT to a problem in TF and P, then SAT is in co-NP, right? That was the state, more or less. Yeah, well, more or less it's
Yeah.
because
No, in other direction probably. If something is complete, then co-NP is equal to NP. That's what you said.
no, I understood that if I can reduce SAT to a problem in TF&P, then NP is equal to co-NP, because then I can prove that there is no solution by providing some solution to this TF&P problem that shows that this thing is not.
Yes, exactly.
Yeah. Okay. But direction is different still. What is written
Yes,
on the board
I'm sure about
not.
this direction. About other direction, I'm not sure.
But Sasha Kazachinsky tried to explain other direction.
No, I haven't explained at all this thing. I haven't. But what if co-NP is equal to NP, then it's complete.
What if co-NP is equal to NP? So what? What is the complete problem in TF and P?
The complete problem will be given formula is give a solution for it satisfying X, or give a proof there is no satisfying
So we take the
assignment.
set which is in NP, complete in NP, satisfiability, and then because it's in co-NP, then there is some polynomial proof for non-satisfiability.
Yes.
And then if we have a complete problem, so this will be a complete problem in TF and P.
Yes, this gives our totality, the fact that co-NP equals NP.
Yep.
So say it again. So we have why it's complete. So we have arbitrary problem in TF.
So yeah, arbitrary problem. We receive input, we interpret it as formula, and then if there is satisfying.
No, I don't understand. So we have some R. So we want to show that SAT is complete in TF.
How to reduce any problem to this?
Yeah, so that's what you're explaining. Yeah.
Yes. Given R.
We have an R of two.
From definition of R, there is a machine V, and you
which
can use it.
Whether XY is good.
Yes, which decides true or not, and we can probably build formula from it in this way.
Sure, but what do we do with the formula then?
Wait, but it's just, I mean, so given an X, we construct a formula. Well, in the usual way. I mean, so I think we just do a reduction. Like, I mean, this R defines a problem
In such way, probably.
Yeah, so we can given X, we can construct a formula phi sub X such that it has a satisfying assignment if and only if, I mean, such that Y satisfies this formula if and only if
V of XY.
Yes.
I mean, but formally, I mean, there is like additional variables that are functions.
Yeah, it's not correct to write. It's just equal. It's, in this way.
Yeah, and then what?
And that's then this is reduction because no, so Y will be
So
we are guaranteed that
TFP
this case will never happen because we reduce R is in TF and P, so it's total. So there is always answer Y such that phi from Y
But I know that then phi
Y.
of y, this formula phi x is always satisfiable.
Yes.
And then makes no sense to set it to we know that it's satisfiable. Then
but we are given a solution to it. I mean, we have to show that from a solution to from satisfying assignment of the formula, we can get a satisfying, I mean, like a solution to the initial TFNP problem.
So the complete problem is not checking satisfiability, but finding a solution, or what?
Finding a solution is that the only.
Finding a certificate that's not true.
Yeah, I mean it's true that every problem in TFNP is reducible to that problem just without the fact that co-NP is equal to NP. It's just that if co-NP is equal to NP, that the problem about finding a solution to SAT is inside the TFNP.
So essentially, we don't need any certificate. We just need the information.
We need a certificate. We need in the reduction, when we have a formula, we need the satisfying assignment from it.
And if there is no satisfying assignment, we can just do nothing.
Yeah, but in the reduction, if we start from a TFNP problem, we will never get a formula, unsatisfiable formula. We will always get a satisfiable formula.
If we start with TFNP.
Yeah, if we start from a TFNP problem, then we always get a formula that is satisfiable, and then moreover, that from any solution we can get a solution to the initial problem.
Yes. Yeah. Last step we need to get from Y solution.
Okay. It looks good, but one should check slowly. But seems okay here.
So, as it was said, it's unlikely that there is complete problems in TFNP, or we just haven't found them yet. But we can consider subclasses in TFNP that are defined by complete problem in them, and there are quite a few of them. Let's start describe a few of them. First, PPP, pigeonhole, polynomial pigeonhole problem. It's principle, not problem. Yes, it's based on this combinatorial principle that if you have function from for example, such format, then there must be collision where say is some circuit. So we can't explicitly give this function, because in this case this task will be not very interesting, because it will lie in FP. Finding answer will be trivial. But when function is represented as implicitly as circuit, we can't find answer quickly, or at least no way known.
No, you should say it more because looking at the circuit, we cannot say whether it never has the value zeros. So I guess the correct state, the correct problem is given C. We should either find a preimage of zero or a collision.
Yes, this is one way to define this problem, or there is equivalent way is just to interpret result of C in a way that if it returns 0 to n's, we can just say no, you returned 1 to n's, for example. So interpreted in the way that it never returns 0 to ends. These approaches are equivalent. Almost equivalent. The class will be the same up to reduction to each other. So another problem, PPA. I do not remember how it translates. In this problem, we are given
Polynomial parity argument.
yes. Well, let's start with picture. We are given even amount of nodes, and we are guaranteed that first node not connected with any. Some of them are split in pairs, and we need to find any node without pair. So in this case, there is 3 answers. Well, now on the language of circuits, we have circuit. And we say that X connected to Y if let's say from X is Y and from Y is X. So if they agree, yes, so if they both say yes, my partner is partner. If they disagree, we say there is no edge between them. And we say that first node never connected to anyone also. Not connected. And the correct answer is any other not connected node. Any X non-zero without pair. So it's similar to PPP. It's easy to see that answer always exists, but finding it's not
and
trivial.
also it's easy to check because
yes,
we just
checking
apply
is
C and get a candidate, and we need to check that this candidate is not.
But wait, I don't understand this example, because it might happen that C of X equals X, and this is not a pair.
But it is also
it
bad.
should
So
be
it's kind
verified if C of X equals X. We say that X not connected, no pair.
Okay.
So there is a combinatorial property of C which says that C square is identity on all non-zero nodes, and it's never has no fixed point, it's undefined on X. Yeah, but it's kind of combinatorial thing which can be checked, which can be disproved by a counterexample. So it's in our class.
So, yeah. Another problem is PLS, polynomial not linear.
Local search.
Local search, yes. Polynomial local search. Let's start from picture again. We have nodes, but now they are numbered. Let's better say it, ordered, and some of them have one outgoing edge, and it must go to the vertex strictly higher number. And some of them do not have such. And we need to find sync in such graph, or also we accept answer that first node have no outgoing edge, such corner case. So we need to find sync. So in this example, answers are 4 and 5, but we can't verify that it's sync. So we return actually not its sync itself, but previous vertex. So answers is 1 and 3 because they lead to things.
So the circuit says for every node whether there exists an edge or if it's
yes, circuit
last.
says similar circuit. And so if it returns number strictly higher, we say there is edge. If it doesn't return number or return less or equal, we say that there is no edge. Oh.
And so why do you say that we cannot check that this is a sink?
In this case, we can, but if we take, for example, 5 as answer, we can check that there is no outgoing nodes, but we also require that there is in node, because last node always have no outgoing, so it's not interesting. Finding node without outgoing
what
is.
Should we find a node without outgoing, but
we should find nodes which have no outgoing edges, but have one ingoing. But in the answer, we return at least one. In answer, we return not this node itself, but this ingoing one. So previous one.
So the answer is the point where we can do one step, but not more.
Yes.
Okay, it's a bit artificial, but probably this equivalent to something else, which is also natural. Okay.
No, it's not artificial. It's similar to gradient descent, so something like this.
But in gradient descent,
So basically, the principle is that every DAG has a sink, and every problem that has a solution due to this principle.
But why we require the sink produced in such? Why we have the DAG which is already topologically ordered? It's a kind of strange.
There are alternative definition in which there are two functions. First function is p, which is not p, which is how good a solution, and second one is graph. And first function for each node gives how good it is, and second one is given a list of neighbors, and this list is guaranteed to be not very big. And solution, any node that is better than any of its neighbors. This is alternative definition of complete problem. No, it's other complete problem. So it explains why it is called local search. We need to find solution which locally optimal.
But it's other complete problem, but it's equivalent to this one. That's what.
Yes.
You're saying. Yeah.
This is one. Yeah. This one just easier to use because it has only one function.
No, but in this problem, do you require that they are numbered sequentially? Or when you say 1, 2, 3, 4, 5?
In this alternative, not.
In the first problem.
In first, yes.
So they numbered from 1 to 2 to the n.
Yes.
But then it's not obvious why this. No, it's not obvious why they are reducible to us. But anyway, let me say something general. So it seems to me that there is a general class of result saying that some existential theorem, for example, like Sperner lemma or fixed point Brouwer theorem or non-existence of a vector field on a discrete sphere which is never goes to some small value, it is continuous. So
Yes.
every topological theorem or many combinatorial theorem are of this type. So, or can be represented, can be checked locally. So they say that something doesn't exist, like mapping without fixed point. And then local, in this setting, it will be, we have a circuit which produces a mapping, gives a mapping, and the answer is the fixed point, approximate fixed point for this circuit. And
Well, Sperner indeed lies in one of TFNP classes, but it's not PLS. It's
yeah. So what I'm saying, that there are many classes,
yes.
many natural problems, and and then probably you can say some, can explain what is the general situation. So for example, in NP class, usually most of the problems are either in P or in NP complete. And here we have a lot of interesting problem which appear naturally in many cases with Satan formula when we need to find a vertex of odd degree, or I don't know, a lot of things. And so what is the general picture? So it's proven for most of them that they are equivalent or not equivalent or what?
Yes, general picture. Here's a general picture. Let's ignore for now red arrows and concentrate on black ones. Black ones show how classes relate to each other. So three described classes do not relate to each other whatsoever. So if it's reducible to one, they aren't reducible to each other. At least there is no known reduction.
Okay,
and
wait a bit. So black, first let's start with simple things. The black arrows are known reductions.
Yes.
And they are just some explicit reductions, and probably usually they are not many of them should be easy as for NP classes sometimes. And maybe some of them are difficult, I don't know.
They are mostly easy.
And for example, kind of Brouwer fixed point theorem is where?
Brouwer fixed point is PPID. Very many problems about fixed problem. Nash is in PPID.
Yeah, and for example, if we consider some theorem saying that there is no vector field on the sphere which is always tangent and never continuous and never goes to zero, it will be where?
I'm not sure. Probably somewhere around here too.
Yeah.
I
Okay.
think so. At least some formulation is also in PPAD. So that there was a paper called something about hairy ball. I think it's the same.
Yeah, hairy ball is exactly the same. Yeah.
Yes. So at least some version is also PPAD complete. In fact, it's interesting that there is a very simple theorem that every natural number greater than 1 has a prime divisor. And nobody knows where it lies, except that it lies in TFNP.
It's related to factoring, of course.
Yes,
so
there is.
It's quite natural that it's difficult.
Yes,
okay.
There is.
So let's return to this picture. So black arrows are known reductions.
Yes.
And then absence of black arrows means that we don't know the reduction.
Yes.
And are there some results which confirm this in a more formal way, that if a reduction exists, then blah 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 is hypothesis is true or false or whatever, or just it's pure unexistence of known reductions?
No, there is. Well, yes, there are black box separations, and this talk will talk about what is black box model. It will be very important. So this red arrows means black box model. separation in black box model.
No, I understand. So there is, if so, there is something, I guess, which you call black box reduction.
Yes.
Which is something, a special class of reduction. When we use something as a black box or whatever, I don't know, but it's just
in
a special class of reduction.
Yes.
And so we can claim that there is at least no black box reduction.
Yes.
But then what is red arrow?
Oh,
For
red
example,
arrows
there is red
says
arrow going from PPAD to PLS.
we proved that there is no black box reduction from PPAD to PLS.
Okay, and still you draw the error in the same direction. It's a bit confusing, but okay.
Where is
No, and the existence of reduction and non-existence of reduction are shown by the arrows in the same direction.
Well, it's red and it's
Okay. You should be no. I cannot. I see that it's red. I cannot claim a Mendelssohn, but it's kind of strange idea. But anyway, but just look. For example, when you see EOPL and UEOPL, there is black reduction in one direction and red reduction in different direction. What does it mean?
it means that there is a reduction from UEOPL to EOPL, but in opposite direction there is no black box reduction from EOPL to
and
UEOPL.
from UEOPL to EOPL, we have a black box reduction.
Yes, we have.
Or not?
There is arrow.
No, black arrows are black box reduction or just reduction?
Just well, actually, they are black box reduction. Almost all reductions are black box.
So the black arrows are black box reductions.
Yes.
Sorry, I missed black box reduction. Have been there? Have you defined
it's
them?
not yet
No,
defined.
not there yet.
Okay.
No, just what I would suggest, if you draw instead of red arrow, you probably should draw a black arrow crossed. Then it will be clear that black arrow in this direction doesn't exist. It will be at least logical.
Yeah, probably.
Okay, but then there are some black arrows of different types. They are thin dotted, does it matter?
Yes, there is two types of red arrows here actually. The first one, how it called?
Какое слово?
Yes,
Dashed.
Что вы хотите
dashed.
сказать?
Yes,
It can be dotted or dashed.
dotted
Is made of dots, and this
dotted
is
means they both all red arrows means that there is no black box reduction, but dashed also means that there is also no randomized black box reduction. Even randomized does not exist. And for dotted, it isn't known yet.
Oh, so there is a lot of unknown things here. So if a black arrow doesn't have anything in the other direction, it's open. That means when you
actually, if we're talking about just black box reduction or absence of them, this picture is complete in a way that from transitivity you can for any pair either deduce that there is a reduction or that there is no reduction black box.
So for example, if SOPL, whatever it is, has a black box reduction to EOPL, then it will be also have a black box reduction to PPA.
To PPA, yes, and this contradicts this.
Yeah. So for black box reduction, we have a full picture.
Yes, picture is full, and moreover, picture is full for all intersections of classes. So, for example, we know that PPA A D not for any intersection classes, we also know that there is either easy reduction or no reduction in black box.
Okay, probably whatever we can learn that for black box reduction, everything and everything is known.
Yes.
And for randomized black box reduction, there are open problems on this picture.
Yes, and what I was doing, I was researching randomized reductions, and what I find out that for some classes, if it's there is no black box reduction from it to some other search problem, then there is actually no randomized reduction from it to this problem. So I highlighted this for classes PPP, PPA, PPADs, and PPAD. For them, this holds. So for them, outgoing usual black box reduction and randomized reductions are the same.
Yeah, so let me say, so there were some open problems.
Yes.
And you solved some of them, and moreover, you proved a general theorem that's saying that for some classes, any randomized reduction can be de-randomized.
Yes.
Yeah. So
I mean, but it's open whether this reduction exists in any case.
Yes, it's only in black box. So we are talking about black box
yeah,
reduction.
but black box randomized model is probably interesting in itself. So you should send this paper to Stock and Fox, no?
I will send it somewhere definitely.
No, it's a kind of major breakthrough. People looked for this for many years, and now you give a general answer.
This is not the case. Usually for black box reduction, this problem are much easier than for regular reduction.
Yeah,
so
for
if it would
reduction,
be for regular reduction, then it would be stopped.
No. But for randomized block reduction, it's still there were open problem, and Fedor solved them. No.
Okay. But
well,
why
it's remarkable, I guess.
It was open for 1 year because full separation was completed 1 year ago.
Just for black box model, it was completed only 1 year ago.
Yes, it's not a very old problem, open problem.
Yeah. So did you already uploaded your paper into archive?
Not yet.
Daniel, why?
You have to hurry up. Yes.
Daniel, why he hasn't uploaded the paper into archive immediately?
It's
okay,
true.
Daniel doesn't have any explanation for that. Okay, let's continue.
No, but I mentioned that you have to write something, that it takes time and so on. Who will do that? That's not easy.
Fedor, I guess? Or
yes.
Danya? Who is his advisor?
Yes, I am his advisor.
Yeah. So then you I'm just it looks like some interesting breakthrough. So at least you should write someone to maybe they will tell that look, it's well known, it's follows from some result of blah 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 in the just
That's
but maybe
the scariest outcome.
No, it's completely normal. That's life. But I think you should just write some. If you cannot write a paper and send it archive in a week, probably you should write to someone at least who works in this domain. Just tell them what is the result and ask whether it's known or not. I guess they will not. They will just answer if they know it.
And if there is a paper on archive, it's easy to write to someone and ask questions because you can give a reference to the text.
Yeah, of course, it's better to do both. But if you know who is working in this field.
For example, John Fearnley, I know, he proves something that some intersection of these classes is equal to something like that PPA intersection with something is equal to something. So for example, you can write to him. I don't know. And I heard that he's a nice guy, at least. So
Okay, you don't risk anyway. He will not.
Yeah.
He's far away and
I will write
cannot beat
in
you. So
chat.
you can no.
Or I can like have his.
But I guess seriously, Danya, if you can write, say that my student Fedor Kiselev did this and this, and I would like to know whether it's interesting, maybe you can say something just in few words, and I guess he will answer.
I believe I can do it myself.
Okay, but this is just a kind of, if you don't do it in a week, Danya should do it. Yeah. Okay.
I thought some bus is like studying this already 30 years.
Yes, first
Yeah.
works on this are from BUS from 98. The first separations here are dated 98, I believe.
Yeah. No, of course, you should read existing literature, but I guess you did this. So if you know that there's it's not in the textbook at least. Sam Bass is an obvious person. He's a very nice guy, and he even has a paper on randomness. So just and he was in St. Petersburg for a semester, and he will be, I guess, delighted to help you. Okay.
So
what is black box model?
Yes, we need to define what is black box model. And actually, in black box model, we redefine not only reduction but classes itself. So what we want to get rid of this circuit. In each definition, we have circuit, and now it will be given as just a long string of exponential length. Well, if it's part of input, it can't be called exponential anymore. Anyways, and we need somehow to define how we work with it.
No, so we just have something which is where is no complexity anymore. Yeah.
Yes, if we
should also define TF and P problem differently. You don't require anymore that something is in polynomial time. No. Yes.
Well, yes, we define TF and P new way. TF and P decision tree.
Yeah.
It's all computation now will be done by decision trees.
Yeah.
So what is it? We say that R is in TF P dt if R is a sequence of R sub n, where R sub n is some subset of sigma n to the power of ln times O(n), where sigma n is alphabet, ln is length of input, and O(n) is a set of outputs. And again, we need two properties. First,
outputs are not now no more strings. They are just
yes, now outputs are just set. We are not interested how they encoded because they are usually short and we can fully read them. So there is no challenge of reading.
So why you consider arbitrary alphabet not binary one? It's important.
It's simpler to work in this way. It's not reduce the amount of. It does not limit us. We still can use binary alphabet, but usually, for example, in TF and P, we have the input will be numbers, each one from 1 to 2 to n minus 1. No, 1 to, no, yes. We have.
Are there some restriction on length ln or not?
Not really. No restrictions. Well, finite. They must be all finite, but that's all.
Okay.
Well, in our cases, for classes PPP, PPA, and so on, they will be small. Maybe the exotic classes where they're very big, but we are not working with those, so there is no problem. So we need totality. Again, for x, there is O such that XO in Rn, for any n. And second, we need very easily verifiable answers. And it means there is a family of trees for each n and each O. There is 3, decision tree. And this 3 and O checks if input x is correct, has answer O is correct for x. So x O in Rn if the n O of x is returns 1. And we require that depth of the tree is limited by some, and here is a slightly unexpected function, family of function, not poly of n, but polylog n, because n is something very big. We can't work with, we don't have so much computation time. We have our computation time is about logarithm of n, so we limit depth by polylog n.
So, but the input is just something of length ln.
Yes. Well, let's say that ln is at least n. It's in all our cases it will be so. So input is very long string, and we can't read it all because this limitation.
And the tree asks for letter in sigma n.
Yes, tree reads letters in these things and gives answer. Is this answer output correct for this x or not?
And the size of sigma n is somehow, we know anything about
not
it?
really limited. Not very important.
Okay.
Well, for example, PPP. I actually complete problems called different way, but to make explanation shorter, I am calling the same way as class. So PPN, for PPN we have sigma n equals just set from 1 to n, from 1 to n minus 1, ln equals just n, and set of answers.
So it's pigeonhole principle.
Yes, pigeonhole principle, and set of answers is just pairs of x, y in 1 to n squared. Well, in the same way, it's easy to see that it's total. Oh, I not defined what is correct answer, but it's obvious. Again, we need to find collision, and it's easy to see that verifying collision in this model also easy. We just need to see what is written in the position x, what is written in the position y, and check if they equal.
Yeah, but then it's obviously unsolvable.
Yes, in black box model, it's easy adversary argument that shows that minimal depth of decisional tree that solves it must be n, because we always can answer in a way that does not reveal the answer. So other classes defined in similar ways. So PPA, we have string which encodes circuit for PPA. For PLS, we have also circuit that encodes circuit. Oh, we have string that encodes circuit for PLS, and so on. So they are translated in this model in very natural way.
But then there is something which I don't understand completely. So you have some classes, and you draw a picture that there is a reduction from this class to this class. And then you told us somehow that there is a stronger notion of reduction, which is black box reduction. And so if there is a black box reduction, there is a normal reduction, yeah?
Not.
No?
Well, yeah, yes, yeah. No,
Somehow. But no, at least informally. And
informally,
now,
yes, yes.
Now you say something strange to me. So you say that let's define a new notion of problem and a new problems. And these problems are somehow informally similar to the old problem, but have no formal connection with them.
Yes, formally there is no connection.
And then you probably will define a black box reduction.
Yes.
For this more new kind of problem. And then you will say that if such a black box reduction exists, then a reduction exists between the older version of the problem. Yeah?
Well, if
a black box reduction exists between, I don't know, ABCD and PQR, then in new sense, then there exists a reduction between the same names ABCD and PQR in the old sense, yeah?
no, in opposite direction. If in usual white box sense there is a reduction, then if we define classes in this way, then between them there will be also reduction.
No, I don't understand. You look at the picture. You know that you said that there are some reductions, but there are no black box reductions. Oh, or no. You said that there are no black box reductions. So normal reduction is stronger than black box reduction, or weaker, more or less.
They can't be compared because normal reduction between normal classes and black box reduction between these classes, but almost always if we have reduction between normal classes, it can be translated into black box reduction between those between corresponding black box classes.
And if we have black box reductions for the new classes, we don't have, there is no way to get a normal reduction for
Not really. In back way, there is too many non-uniformity in this model. It's hard to translate backward.
Okay. So, but it is not a theorem. The existence of reduction in normal model doesn't imply, because even you cannot define the classes.
Yes, there is no strict definition of corresponding class. Black box class that corresponds to some white box class. Yes, there is no strict definition. What is it?
Okay, it's kind of confusing for me. So there are, you compare two notions, but they define for different classes, and it's not clear in which direction one is, in which sense one is stronger than another. Still somehow No, so usually,
Probably if
usually,
you like require something additional from black box reduction that is effective or something, then it can be converted into a normal reduction. No?
Yeah, probably if we require that, for example, so this that this check can be actually done not with trees but with the machine.
so this tree can be implemented by a machine?
Yes. Then most likely it can be converted backwards.
I still have trouble understanding the definition. So can you say what is the trees for the class PPP?
Tree for class PPP. So answer is a pair of X and Y, and tree first asks what is written in the position X.
So you just let me say you have a function which is written just by the list of values.
Yes.
And the answer is a point where the collision happens. And to check that the answer is correct, you need just to read two values in this list where the collisions claim to happen. And then you know whether it happens or not.
Yes.
So O is the answer.
O is the answers, output.
Output.
Yeah. And so how does it depend? So what is N in this example?
N is the size of the set of pigeons, and the size of holes is N minus 1. And so the list of where the first pigeon goes, where the second pigeon goes, and so on, they are just number between N minus 1.
Yeah, so N numbers from 1 to N minus 1.
So we have N holes, N minus 1 holes, and N pigeons. And the descriptions who goes where is just a string of length N in the alphabet of length N minus 1. No, Bruno, something trivial is ask again.
Yeah. So, but I still have trouble. So, for one circuit, there is one value of N and many values of O.
No.
So, in the original
family
problem,
of problems. Nth problem is the problem for N pigeons and N minus 1 holes. For every N, we have a problem for N pigeons.
Well, I drew a simple example for N
just
equals
wait a
5.
bit. Just, Bruno.
yeah, but I have trouble understanding. So, Rn will be set of pairs.
Yeah, the first element of the pair, the input, is just
goes.
the description of where pigeons are going. The
Yeah.
second element of the pair, the output, is the numbers of pigeons which meet in one hole.
Yeah.
So, as Fedor is saying, the input is, for example, N is 5. Then we have 5 pigeons. And imagine
So
that this is the one of the possible inputs.
yeah, but this is the circuit version. I understood. And
No circuits. We have just the string.
Yeah.
And the output for this example, there is only one, or actually two outputs. 1 4 and 4 1. It's collision.
Yeah.
And what he's saying that indeed, if we want to check the answer when this input is given as an oracle, we still can do it very fast. We need to check that there is indeed a collision in 2 points.
Yeah, this is clear. So I understood the
then?
previous variant of the problem with circuits, but in this definition, I don't understand what is the tree.
No, decision tree is a machine Which
Yeah, I
reads.
know what is a decision tree, but
Okay.
I don't know in this example with 1, 3, 2, 1 in the bottom,
Yeah.
what is the tree in this example?
The tree in the first you ask.
So tree depend on O.
For
Three
every
queries
output,
positions.
there is a tree. For every output, there is a tree.
Yeah.
So for output 1, 4, there will be a tree which first asks the first position and then asks the fourth position and then gives the answer. It will be a tree of depth 2. If I understand correctly.
Yes.
Okay. Yeah. Oh, so all the trees are of depth 2.
Yeah. So O is somehow not questioned in decision tree. O is given in full in the beginning of the tree. For every possible output, we have a separate tree on inputs.
Okay. Yeah. So, yeah.
Well,
Also, formally, we should add that if x equals to y, then the tree should be constantly 0.
yes. And x not equals y.
Okay, well, it may be added here, but also we can say that if they are equal to each other, then we just give a trivial tree that is always 0.
Well, yes, we can in this way implement it. Or just remove pairs which match. We can define ON in any way we want.
Okay, I think I understand. But in all your examples, then 3 are not deep.
Yes.
Right?
That's
Yeah.
exactly the requirement for.
Yeah, we require it to
problem.
be.
No, I
small.
mean bounded by a constant. So for PPA, so because all the problems involved just like so for PPA, how deep is the tree?
Yeah, for PPA it's also 2 because we need to ask about.
2
It's
questions.
yes, 2 questions. Neighbor and then ask the neighbor of neighbor, and if it doesn't match, or if we after the first question we hit ourselves, we say we are alone.
Yeah, and PLS it may be depth 3.
PLS, we ask where we go, and then for this we also ask where we go, and if it seems to be depth 2.
Depth 2, okay. Yeah, I understand.
So now we need reductions. For reduction, we also have F and G, but now they also made using decision trees, not machines. And first, let's define reduction from some Rn to Sm. No, picture is similar. If we have X, we can transform it.
Sorry, you reduce individual instances for fixed n and m, or you reduce the sequence of problems?
First, we define for individual.
Okay.
Yeah, for fixed and m. So if we have X, we can compute new inputs in a way that any symbol is y equals y1, y2, and so on. And each position can be computed usually using 3. So we have F1, F2. So actually F is not 1 tree. It's family of trees. Family of decision trees. And G also will be family of decision trees. So for each position, we have a decision tree computing value in this position, querying X in process. So queries, is 2x. So we receive y in this, when we can construct y in this way, and then if we somehow get our hands on answer for this y, we then can use G to construct answer for original task. For original search problem, we can use JO from X, so that X JO from X lies in Rn.
But what is assumed about this complexity of this last thing? Just any mapping, or it should be some also some
Well,
small
we
decision
also
tree,
require
or...
that depths, all depths of trees are also limited by polylog.
But what does it mean? We have
well, yes, for fixed it doesn't mean anything. Let's so for fixed there is always reduction. Let's go to not fixed values.
No, I didn't. So for no, there is kind of a notion of complexity, which is just the complexity of length, depth of trees for F1, Fn. But the question is, for the last mapping, do we also have a tree?
We have G, a family of 3 G. For each O, we have 3 GO. This is decision tree. GO. Each new one for each O.
So O output is given as some abstract object. So we don't query it in any way. It's known
already inside
and
tree.
Depending on this output, we have some tree which provides the solution for original problem.
Yes.
And why not all problems from TF&P decision tree cannot be reduced to each other by this definition? I mean, we can always ask F to just solve it, right? Because it's just bounded by polylog.
Well, we haven't finished defining because we only for fixed n defined.
Okay.
And for sequence, we say that R is reducible to S if there is M from N such that Rn reducible to Sm by reduction of depths polylog n. And also for transitivity, we require that M also is bounded in by quite a big value, but still by this value.
Just can you repeat the question? There was some question. Just ask the question again.
Yeah, so why we cannot just take F and ask it to solve our problem?
Because we allowed only polylog of n queries, and problem have a string of lengths ln, which at least n in length, and polylog n is usually less.
So f is an arbitrary function. Every position in f of x should be a simple function of x.
But I mean, if R and S,
function of x.
If both R and S are in TF&P decision tree, then there is a reduction, right?
No.
No.
We say that the output can check. There are two things: to check the output and to produce the output.
Mm-hmm.
And in black box model, in decision tree models, they have different complexity. For example, to check that there is a collision somewhere, it's easy. You need to check only points when the collision is claimed to be.
Yes.
And to find the collision, you need to look at all values of x, or almost all values of x. So checking answer and producing answer have different complexity in decision tree model.
Oh, so maybe I didn't get, how do we get Y and O from the reduction? Yeah, here on the right side.
Reduction, no, we do not get Y from the reduction. We transform X to Y.
Yes, if we're
using
given
decision
X,
trees.
we
Yes,
can
yes.
use decision trees to...
Let's say simple if it has a small decision tree.
Mm-hmm.
And then if we know some output for this new problem, then we can compute the output for X with a simple decision tree, which depends on this output. This if I understand correctly.
Okay, and could you please also say what do we want to say with this reduction? I mean, usually we want our reduction works like if we can reduce A to B, and for example B is in P, then A is also in P. I mean, yeah. So could you please state something like that for this kind of reduction? What do you want to say by that?
No, I guess
this reduction means if we can solve this efficiently, then we would be, if we have someone who solves it for us, we also will be able to solve this.
Efficient solving means that there we can produce the output using a small number of queries to the string Y.
Yeah, so that this problem belongs to TF&P decision tree.
No.
Well, RNS.
TF&P is just the search problems. And
no, I mean above you wrote TF&P with DT like upper script.
No, yes. There is a confusion. When we have TF&P, it's just a class of problems, and some of them are easy, and there is no name for this. There are trivial problems solvable problems in TF&P, and I guess that solvable problems means that we can produce the output using a small decision tree on the input.
Yes.
I don't know. Fedor can confirm if you. No, it's just my fantasy. But
yes. So everything
natural to believe.
True.
So for example,
probably Just ask again.
Yeah, for example, PPP belongs to we have small decision tree for PPP.
No. We have PPP belongs to the class means that there is small decision tree for checking the answer for PPP.
Okay, it's for checking and finding. Okay,
it's the same problem as for normal and P. We have a simple algorithm to check whether Y is the solution, a good answer for X. But the question which we are really interested in is to provide the answer given X.
Okay, yeah, now I got it.
Here we have also... Okay.
Yeah, thank you.
Well, I should probably demonstrate why this model is... how in this model we can produce proofs that one thing is not reducible to other to demonstrate its power. I think simplest two classes to prove it is that PPP is not reducible to PLS. It's
pigeonhole and what is the second?
Local search.
And local search is this a strange story with integers?
Yes.
And then the string is just for every n you have some bigger integer, and you need to find an integer which can or just the word nothing.
Yes.
And then you need to find, given a string of this, you need to find. Okay, maybe you should start with a simple thing and to show that something is reducible to something. I think it should be easier, and we probably will not understand even this easier thing. So let's try with easier thing.
Okay, let's start from easier, but I haven't introduced any classes that are reducible because I introduced only...
PLS is not reducible to PPP either.
Yeah. In picture, three classes I introduced are pairwise irreducible to each other. So I need...
just introduce two classes which are reducible and show us the reduction.
Yes, let's introduce, for example, PPADS.
Oh God, yeah. 5 letters, so they probably mean something. What do they mean? Daniel, you know what they mean?
Polynomial parity argument directed version about sync.
Yes, it's
Okay,
PPA
okay.
plus directed plus sync.
Yeah, directed and sync. Okay.
So what we have, it can be defined in white box setting, black box setting. We have graph, and
Don't tell us about white box. We are terrified enough.
no, okay, black box, and where and this graph have in and out degrees at most 1, and for each vertex we have we can find out where it leads and where from it have.
Yeah. So the graph is representative of a string. So
Yes.
the vertices are numbered from 1 to n, and for every vertex we just have two letters in our word: the predecessor and the successor.
Yes.
Or the information that they do not exist.
Yes, and we say that the edge really exists if both vertices agree on this edge, meaning that out of U is where and out of where is U. If they disagree, we say there is no edge. And also, we are guaranteed that there is no edges to the first special one, selected one, let's call it first. We guarantee that there is no edges going to it and there is outgoing edge. Or we can accept as answer anything contradicting this.
Yeah.
So it is a matching, right? Because we have only one output for each node.
Say it again.
I mean, so here it is written out of U is V and out of V is U. So it is a matching.
Yes,
no. It means that we have for every vertex, we have a list. We have a list of two the successor and predecessor.
Okay, so it should be
It's
out
in.
Okay.
Yeah,
Thank you.
Correct.
Okay. No, if now I understand what is notation. Yeah. Okay, so this is easy to check in the stream model, because if we have the V, then we can look there and see whether it's U. So we can cheaply assume that graph is consistent in this way.
Yes, it's easy to check consistency and find out what really is there really outgoing edge or not. And
so Andrei Rameshenko kindly tells us that we are already 1 hour and a half, so you should decide when it's you can finish something. I guess it will be a good idea, but then you will have the chance to continue.
Yes, I will finish this and probably wrap up with some questions and so on.
Okay.
So we have some graph.
So we have something which has only outgoing edge, and then you should have something which has only incoming edge.
Yes, the answer is on this picture. There's only one answer. Any node which sync. There is incoming, but no outcoming.
But also there is another thing on this picture. Why you say that it's only answer?
Yes, there is actually there's two answer here and here.
Yeah.
So, but not this. This one not considered answer. There is a similar problem PPID. In PPID, this one considered answer. So we either sync or source different from one.
If we don't need PPAD, let's not mix
so
we want a sync, yeah.
let's prove that PPADS
Yeah.
is reducible to PPP.
So we can prove this theorem
Uh,
using pigeonhole principle, so to say.
yes. Well, we need to define F and G. Well, let's start from picture. We can actually see that it's very similar to PPP in a way that we had outgoing edges only from all vertices, but incoming edges can be only for these ones, and first one can't have incoming edges.
Okay, so we have a graph. Who are the pigeons and where they fly?
So pigeons are all vertices,
Yeah.
and the boxes are all vertices except first one.
And then just whatever whatever two pigeons go in the same place, we get a.
Well, yeah, we will have that for some vertices there is no outgoing edge, then we can arbitrarily set it, and then if we find answer, we can run back, recheck if really this vertex has this edge outgoing or not.
I think we can map them to themselves.
Oh yeah, we can.
So it is the same as a loop.
It can interfere with incoming edges. When we say that loop, then it means that vertex says that out of this vertex is this vertex, and in of this vertex is this vertex.
Okay, but
okay.
we can think about this as a kind of homework. So the general idea that there is some kind of reduction from the problem of finding the thing to the problem of finding a collision for pigeon. But also it's important that the reduction is local. So when we describe how pigeons flying, it's only, we need only ask several few places in our original graph.
Yes.
Yeah.
And in this example, constant.
And then
but...
knowing the output, we can just say what, maybe after some simple checks, we can say what is the output for this PPADS.
Yes.
Yeah. Okay, so it looks like it should be simple, but probably we can try to work out the details ourselves. And no, I can just say what is the main kind of misunderstanding somehow, why it's so difficult to follow you, because we are always not sure how robust are the things. So you say we can do this or we can do that or we can define in this way, and you choose some definition. But for us, it looks like there are several ways to choose a definition, and that's not clear why they would choose. Either it's because it's the most natural way, or because the others are equivalent to it. So it's kind of unclear thing here.
Well, yes.
Yeah.
There is.
Yeah, but then maybe then next time you can, you know, when people speak about computability, they need some feeling that something is computable or something is not computable, so you can think about, describe the algorithm informally, and people do not worry whether it's really implementable, and they see that it's more or less the same. And here we don't have this feeling, and so we have an intuitive idea of existential theorem, that given something we can find some local inconsistency, it's non-existent theorem. Given something, we can find the local inconsistency. And they have some versions, and one would like to be sure that all these versions are equivalent, or be aware that some natural theorems have non-equivalent versions and so on. And
Well,
maybe this can be this problem can be treated next time. That's request.
Well, it's usually requires a lot of experience, a bit of experience in this field to understand what changes to
So
problems
you say that,
can be made.
There is no hope, and we should not come to your talk. Okay, but,
No, there is hope.
If there is hope, then maybe you can try.
I'll
No, just
try.
because several important people have to leave, so probably we should not. They already left. We should
Okay.
not. We should not do it now. But it's indeed it's a very natural thing. Let me also add something. So there are also a lot of problems considered in other settings. There is something which is called Weyrauch reduction problems. So, for example, there is the Brouwer fixed point theorem and kind of some other topological theorem. There is kind of Weyrauch reduction when we speak about infinite objects, and when we transform the question to question by a continuous or computable mapping, and then transform the answer into an answer by continuous or computable mapping, and there is some classification. And there is also a classification in terms of reverse mathematics. You add an axiom saying that there always is something, and you look whether you can prove a theorem that there exists for another model. And also there is an oracle setting. You have an oracle to compute something is computable, to compute something, and then you ask for an oracle to compute something else. And it seems that all these classifications are somehow, for some strange reason, they are close, but they are not exactly the same. And also there is probably there is something like Turing reduction, when you can do something twice, so there is a kind of general picture which is quite confusing. So if you can kind of explain what is known in general about this classification of theorems and all these different approaches and how they are connected, or maybe they are not connected at all, or whatever, this will be also very interesting, at least for me. And then probably we can invite some very clever people who do these reductions in Weyrauch sense and other sense, and maybe they also can say something about these things. I guess Laurent is the first candidate, but if we are good enough, maybe even Ludovic Paté can come and say something, or just any other experts. It would be very interesting to compare what is happening. I think it's an interesting topic.
No, I'm not really familiar with those reductions.
Oh, but okay. now yes, but maybe later you will tell us something. The best way to learn something is to teach someone. So why not to try? But anyway, still the most important things for now is to write something to Sembas in a week, I guess. Even if you have some completely incomprehensible paper in the archive, it's also not so bad. You can replace it with something readable later.
I'll try. Maybe not Bus. I have other people in mind.
Okay, but just do it.
So I think for the talk it would help to understand some easier question than the PADS P2 PPP reduction. For example, what is black box definition of TFNP and why PPP is in TFNP? It's probably very easy, but by telling it, it helps us to understand better.
No, why PPP is in TFNP?
In the black box model, of course, in origin circuits,
No,
but verified it's easy.
It's not in TFNP. It's just a completely new type of problem. It's in TFNP DT
Yeah.
or whatever.
So what is
Decision tree.
TFNP DT? And so I can guess it, what it is.
No, it was defined. It's just
defined.
this relation which is checkable in small depth.
Yeah. So
And
yeah.
we try to. It's one of the things which I think I understand why PPP in this class, because the potential answer, which is the collision,
Sorry,
can
okay.
be checked easily by blah 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 blah.
Yeah, so forget about my stupid remark. Sorry.
No,
I think
no.
confusion comes from
just
the
a good teacher should will be especially attentive to stupid remarks, because then he can understand what he should be explaining. So don't please do all the stupid remarks you can, and this will be very useful for the speaker.
I think the source of confusion is that I call PPP is both class and complete problem in this class, some overload. But TFNP is just class. There is no complete problem in TFNP, even in black box setting. Maybe this is the source of confusion.
Last, I don't understand at all. But no, it's so I think that just you can say that, consider some problem like pigeonhole, and then we have different settings. We can have this polynomial time setting. We can have his black box decision tree setting, and then somehow you want us to agree intuitively that they somehow represent the same idea, and then you should define reducibility, black box and non-black box, and somehow it's strangely you claim that even if the problems are different, still the black box reducibility often gives a reducibility for non-black box version. This is the main thing which you somehow is obvious for you but very strange for us.
Usually in opposite way, in normal reducibility.
So usually the normal reduction. Usually the normal reduction is at the same time producing a black box reduction. That's what you're saying.
Yes.
But there is no reason to expect that any normal reduction will produce a black box reduction.
No, because there is no formal definition of corresponding black box problem.
But it can happen. Are there some example when you know normal reduction, but you don't know a decision tree black box reduction for natural counterparts?
Well, for some classes there is a complete problem which does not have circuit. For example, for PPAD, where Brouwer, Sperner, and so on, there is also Nash, which complete problem which just input is just, it's a game for two players. Input is stable of.
And you want to find Nash equilibrium. Okay, this is, should be explained.
And it doesn't have circuit. Is finite, explicitly given.
So this problem doesn't have any black box version.
Yes.
But why? Why cannot you just ask for finding the Nash equilibrium? Why it's interesting. What is bad in this problem? It looks like existential question. Why it's not suitable for black box setting?
Well, black box usually constructed by replacing all circuits with long strings, but there we have no circuits.
No, but the string is just a table.
The table is a very short string. So there is an underlying graph of all strategy profiles with some probabilities.
So what? What is the problem? Oh, it's kind of strange, because usually you say that, look, there is a problem, we replace everything by some finite string and blah, blah, blah. And here you suddenly say that, no, it's not possible. So what is so bad about this problem?
Well, usually there is an exponential string and some small circuit that produces this string.
And in Nash?
And in Nash, there is no explicit circuit. So the
table is not exponential.
No, small table.
The table is not exponential.
So we have a polynomial table, and
yes, we have a
difference. There is no big object. So it's already given by, okay. So usually we have some big object defined by circuit, and in Nash we have no big object at all.
Yes.
But still it's strangely it's PPA. It's complete in this PPAD thing.
Yes, it was a surprise when it was discovered.
And you know why it's complete?
Well, it's a long proof.
Okay. No, just yes or no. You know this proof or not?
No.
No. Okay.
I know.
Danya, and you know this proof?
Well, I know it in general, but not in all details.
Okay. Is there anyone who really knows this proof in the room? Okay.
Well,
no volunteers. Kolya, you know the proof or
no,
not?
No.
Okay.
I'm sorry,
Everyone is in the same. Okay. Not. We are even more stupid than you, but. Okay. And
I can.
It's some theorem, just like I don't know, like PPP or Hastad theorem. It's very complicated, or it's still manageable.
It's manageable. Well,
but you didn't manage it. Okay.
I heard it. I already forgot.
Well,
but it's not like PCP theorem.
Not like PCP, but well, it's not very difficult, but it is complex. So there are.
So there is a gadget of 17 objects which connected by 21 arrows and blah 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 blah.
Yeah, something like this.
Yeah.
So because the idea is that you should, you should model some, you should model the search for a fixed point by some game. And so you must guarantee then that any equilibrium in this game corresponds to some fixed point of the initial function.
But the game is somehow small. The game is small if the original function is defined by a small circuit. This is what is non-trivial.
Yes.
So in this reduction, we took circuit and we look inside it. It's not a reduction from some other PPAD problem to Nash. Is not black box in a way, abstractly black box in a way that we look inside the circuit. We actually interested how it works. We look inside, take it apart, and use this to construct the problem.
Yes, Yes, at large scale, for every gate of the circuit, we consider some small game with some players who somehow copy the computation of this gate. So they compute, so conjunctions, disjunctions, and so on. And so we obtain a game with a very, very large number of players. And then we model this large game with some game of small number of players. So the general architecture is like this.
No, it would be nice if at some point we can look more at this. It's very indeed for a long time I just wanted to understand all this story, and especially the connection with infinite case, which is mystery, and in many infinite cases there are also black box reduction, and not just you can ask whether there is a continuous mapping which does something, and separately you can ask whether there is a computable mapping which does something, and so on. So if it's just a philosophic, if our interest is philosophic, saying that not all existential theorems are the same, and some are more existential than others, it will be interesting that we can understand it in different settings, and whether we get the same classification or not the same classification. Yeah. Okay. So many thanks for the speaker, and you're in a difficult position. You need to fight with the audience and the English language at the same time.
And the board.
Yeah, and the board. Yeah. And Daniel should explain you how all English letters are pronounced. So you shouldn't say X and Y. Either you say X and Y, or you say X and Y, to be consistent. And so on. But this really is interesting topic, and we would like to learn more, I guess.
Do we have time for one more question, or?
Yeah, sure.
Of course, if someone starts, he can just go away. Since it's online, there is no problem.
Yeah, so as I got it, your main result was to show that some reductions can be de-randomized, right?
Yes.
And how the decision tree is related to it? I didn't get the point.
So there was no definition of randomized reduction.
Yeah, we even haven't even started with the randomized reduction.
But it's related, right? Or...
Yes, it's related. It's instead of one pair of FG, we have some distribution on pairs, and we want probability of success at least 1 over polylog n. Success is that if we take X and apply F, and then take worst case O, and then apply G, then we must receive a correct answer.
Oh, you mean the reduction, randomized reduction also uses decision tree?
Yes.
No, it's just a distribution on normal reductions, I guess, yeah?
Yes.
And how the reduction with decision tree is related to just a normal reduction we've seen above?
With what?
I mean, is it, so we had a black box reduction, or not? I forgot what we had above. We had a definition of a reduction inside the FNP, right?
We had reductions for normal problems, not decision tree problems.
Yes.
Well, you can define randomized for normal classes also in the same way.
But your result is for decision trees.
Yes.
Okay.
Again, in this case, we can't separate anything because it would imply P not equal NP if we separate any two classes here.
No, but still, if you prove that existence of randomized reduction between some classes implies the existence of normal reduction, it probably will not not in black box, in standard model, it will
Yes.
not give some immediately give something
No.
like P equals to NP or BDP equals to P or whatever.
No, well, in standard model, it does not translate into standard model, this derandomization.
Yeah, but you said something that if there was a derandomization standard model, it would imply something unbelievably to prove. And
well, yes, derandomization wouldn't imply. Maybe it's possible in this case too.
То есть, в принципе, ну, Бруно left, в принципе, такой результат можно себе представить для обычной модели, но, конечно, он таким способом, видимо, не получается.
Да, я
и
очень
то, что
сомневаюсь, что он
делаете...
получится таким способом.
Да.
А то есть все-таки обычно исследуют как раз-таки сведения вот внутри всех этих классов TFNP, исследуют какого рода сведения обычно? Обычные или decision tree?
Сейчас.
Обычно вот те сведения, которые существуют, как я понимаю, они как бы имеются в двух версиях. Они, во-первых, обычные, а во-вторых, decision tree, и конструкция более или менее неформально одна и та же.
Да.
Ага. И у нас нет прям формального, в смысле, мы не можем, например, сказать, что decision tree строго слабее, например.
Не можем, потому что это между другими объектами.
Ну вот, да, хорошо.
И нет формальной связи. Вот мы говорим, что вот это, ну, так сказать, вот в этом мире там вот вместо там лошади пони, но это, так сказать, не формально. Вот нам кажется, что они похожи.
Да, хорошо. А когда говорилось, например, что там, если для TFNP есть полная задача, то есть мы в какой-то момент, кажется, оперировали в одном предложении задачи из TFNP и задачи из класса NP. Хотя это тоже как бы разные объекты. Там вначале было про...
Это я внес путаницу там в другую сторону. Что, ну, если мы
во все
NP...
стороны, так что ничего страшного. Но...
Сейчас, там вот было два утверждения. Первое, что если мы NP можем свести к TFNP в обычном смысле.
Вот это странное утверждение.
Нет,
тоже.
там вообще было NP, которые вообще не пришли кобыле хвост, оно вообще из другого класса. То есть
из другого, но сводимость можно определить.
Нет, но это будет отдельная сводимость, которая не совпадает ни с одной из двух уже имеющихся.
Да, это какая-то другая сводимость, да, ну можно.
Нет, ну, конечно, это не то самое, как это самое. Тоже не придавало ясности наличие еще отдельной сводимости. Нет, в общем, что-то мы поняли, и большое вам спасибо за это, но, как вы видите, поняли мы плохо, и надо еще растолковывать подробнее.
Так, а в следующий раз переносом там что-то меняется семинар за перенос выходных? Или он на субботу переносится?
Переноса выходных я в понедельник буду в дороге, поэтому я, так сказать, кровно заинтересован в том, чтобы было либо в субботу, либо уже до следующей недели, где я...
Слушайте, лучше следующий понедельник вообще отменить, потому что у нас все разъедутся более-менее. Ну, будут отдыхать. Понедельник.
И, то есть даже субботу, переносить на субботу, видимо, было бы тоже неправильно, потому что... Это...
Ну да, не очень удобно, конечно, переносить на субботу.
Да. Нет, ну вообще ты теперь как бы на пенсии французский, так что...
Ну ты-то на пенсии, а мы-то еще нет.
Нет, ну ты так мог бы, да. Нет, я еще тоже нет. Но это самое. Хорошо. Так что, тогда через 2 недели вы тогда...
Да, через 2 недели. И я бы, кстати, советовал это самое. Сосредоточиться просто на доказательствах, без всякой этой фигни, жвачки про взаимоотношения моделей. Ну давайте просто забудем. Давайте забудем.
Нет, все-таки если уж мы начали про это, по-моему, это интересно. Нет, это самое, может быть,
можно просто узнать, почему там одно не сводится к другому, а там, где сводится, сводится. Именно в этой модели decision trees с деревьями решений.
Нет, если действительно результаты, которые вы можете доказать, все относятся к модели decision trees, то, может быть, действительно, поскольку мы уже поговорили философски про это, можно в следующий раз снова начать, как ни в чем не бывало, как если бы этого занятия не было, но начать с decision trees. Как вам такой план?
Я за.
И доказать, что что-нибудь сводится, что вот повторить доказательство, что что-нибудь сводится, повторить доказательство, что не сводится, дать там какие-то упражнения, что вот есть такая теорема, как выглядит, чтобы мы прямо сразу сказали, как выглядит соответствующая задача в decision trees, и убедившись, что мы все это понимаем, доказать после этого вашу замечательную теорему, которая к этому времени уже будет одобрена или не одобрена заграничными коллегами, которые этим занимаются, и это самое. Мы все равно ее послушаем, даже если она будет не одобрена, они скажут, что это давно известно в работе там кого-нибудь.
Не, ну это давно известно, потому что даже разделения не рандомизированные, они какие-то недавние.
Нет,
Да,
в сути результат, что рандомизировано, о дерандомизации в принципе так может быть отдельно. А если
Да,
в одной фразе, то можно ли каким-нибудь словом сказать, какая там техника дерандомизации?
Эти классы, они такие очень красивые в том плане, что если ты, например, про ПВП знаешь уже несколько ребер, и там не нашлось коллизии, то задача просто превратилась в задачу чуть поменьше. То есть такая рекурсивность.
То есть там не используются никакие там экспандеры,
Не, никаких экстракторов.
дисперсоры, вот вся
Нет.
эта страшная наука. То есть это какая-то, то есть есть надежда что-то понять в вашем доказательстве.
Да, там самое сложное определениями разобраться, наверное.
Ну хорошо, нет, но это уж вы постарайтесь тогда нас просветить по части определений. Да. Ну хорошо, в общем, мы вас не очень достали, нет?
Нет.
Нет, нормально, хорошо,
У
ладно.
меня даже ромашковый чай не закончился.
Да. Ладно, спасибо еще раз. И тогда, значит, до встречи через 2 недели. И, наверное, тогда вы разошлите по списку просто аннотацию, что вот как бы если бы даже этого доклада не было, и напишите там, что это самое можно понимать независимо будет вот про это.
Сейчас подкорректировать аннотацию теперь, что мы начинаем сразу с Black Box.
Нет, ну да, сказать, что мы обсуждали там это будет продолжение, но мы начнем сначала и рассмотрим Black Box там, и может быть что-нибудь докажем. В худшем случае просто сводимость, в лучшем не сводимость, а в еще лучшем дерандомизацию.
Ну да, примерно так и будет. Хорошо.
Ну хорошо, ладно, сейчас с вами напишем.
Да.